Turing 6502, Jump and Branch. I'm Dr. Matt Regan. This is the block diagram for our Turing 6502 that we've previously developed in this playlist. And now we're getting to the point where the rubber meets the road. This is the fetch, decode, execute cycle from the last video. And this really is the beating heart of the machine. Here, we're just executing the set decimal instruction over and over again. But in this video, we're going to start looking at some more complex specific instructions. Now, do you remember that I modified the fetch cycle to increment the program counter before reading the next instruction from system memory? If we look at our equivalent C code, we can see this in the first line after the while. And it begs a very good question. Why increment the program counter before fetch? Well, let's look at the first 20 million instructions after the set decimal mode at 7AF5. We see that the Apple Win emulator, which is cycle accurate, requires 57 million clocks. This is just under 3 clocks per 6502 instruction. And this seems reasonable given that the shorter 6502 instructions require 2 clocks. My first implementation of the Turing 6502 actually required 260 million clocks for the same code. But after some optimization, particularly around fetch, I was able to get that number down to 140 million, and that's because fetch occurs for every instruction. So we went from 4.5 clocks per 6502 clock down to 2.5 clocks per 6502 clock. And with this current Turing 6502 design, we'll never get down to 1 clock per 6502 clock. That's because the real CPU overlaps fetch, decode, and execute, and it does this with extra hardware. But we'll explore these ideas more in the Pure Turing playlist, which is coming soon. So here's the full list of 6502 instructions. We're going to go over all of these in future videos. Of these instructions, these are the ones that may modify EAH or EAL, and these are the ones that require full fetch. That is, at the end of these instructions, they need to jump to full fetch for the next fetch, decode, execute cycle. But these instructions are guaranteed to end with PCH in the MAR high flip-flops, and therefore they can use fast fetch in the next cycle. We have these remaining instructions that don't need to increment the program counter before fetching from main memory. These instructions set up the fetch, then jump to Rule 28 directly. In this video, I'm going to go over the jump instruction and the branch instructions. I'm going to add an auto increment flag to our C model for the fetch, decode, execute cycle. Normally this value is set, so the program counter is pre-incremented before the fetch. But after a jump or a branch, the program counter already points at the next instruction, so we don't want this pre-increment to occur. But this isn't true for all instructions that modify the program counter. For example, the return from subroutine instruction requires this pre-increment before the next fetch, so this really has to be done on a case-by-case basis. So let's look at the jump instruction, which is an unconditional jump. That means it changes the flow of the program execution every time it's reached, no matter what. This instruction takes 3 bytes in main memory. The first byte, called the opcode, is the value 4C in hexadecimal, then it's followed by 2 bytes which form the destination address. Now it's stored in what's called little endian form, and there are endian wars all over the internet. But basically what it means is the PCL address is stored first and the PCH address is stored second. Again, back to our C equivalent code, we see that there's an entry in the switch statement for 04C hexadecimal, which causes the jump code to be executed. From a Turing 6502 perspective, we see an arc out of Rule 28 which leads to the jump absolute instruction rules. Let's look at a practical example. This is the first jump instruction encountered in the Pac-Man code, which is located at 7BE0. And these are the instructions before the jump. Again, don't worry too much if you're not familiar with 6502 assembler language. We'll go over these instructions in later videos. Immediately after the jump instruction itself, the following 2 bytes at location 7BE1 and 7BE2 tell us where to jump to. So what we want to have happen is that the BC at location 7BE1 gets copied into the PCL register variable. Then we want the 7b at location 7BE2 to be loaded into the PCH register variable. So what this means is the next instruction fetch after the jump occurs at location 7BBC and not 7BE3. I'm going to show here what we're trying to achieve with the jump instruction. We enter the code with the program counter pointing at the jump instruction itself. So the first thing we need to do is increment the program counter and point to the first part of the new address. Then we read this value and we need to store it somewhere. I can't just put it directly into the PCL variable because we still need to use the current PCL to fetch the second part of the new address. So I'm going to temporarily store it in the EBL variable. Now that I have the lower 8 bits of the new address, I need to go and fetch the upper 8 bits. Again, I increment the program counter, but after this read, I don't need to use the current value in the program counter anymore, so I can load this new value directly into the PCH variable. Now we have the upper byte of the new address in the PCH variable, and the lower byte in the EBL variable. Now all we need to do is transfer EBL into PCL. The PCH variable and PCL variable hold the address of the next instruction. So we don't want the auto increment during the next fetch cycle. Thus, we set auto increment to false, and the next fetch will be from the location currently in the program counter variables. Now let's see how we might encode this jump instruction into the Turing 6502 rulebook. The first two rules, 5654 and 5655, just increment the program counter, and we've seen this before in the fetch cycle. Next, we prepare for a main memory read, and we point the 6502 notepad address pointer to the EBL variable. So then, in rule 5656, we load the lower byte of the new address from the main memory into the EBL variable. Rules 5657 and 5658 just increment the program counter again. We read the value from main memory into PCH and prepare to do the transfer from EBL to PCL. But
Houston, we have a problem.
From our original definition of a Turing machine, when we're using the 6502 notepad, we have to read and write from the same location. We can't just read from one 6502 notepad location and write to a different location in the one clock cycle. It seems like Alan Turing foresaw this problem and suggested a solution in the paper. The scan symbol is the only one which the machine is, so to speak, directly aware. However, by altering its M configuration, the machine can effectively remember some of the symbols which it has seen previously. So what we do at rule 5660 is incorporate the value seen in EBL into the next rule number. So if I'm in rule 5662, then I know the value in EBL was 1. If I'm in rule 5916, then I know the value in the EBL was 255, or FF hexadecimal, because 5661 plus 255 equals 5916. This is effectively what Turing meant in that paragraph. By altering the M configuration, the machine can effectively remember a previously seen symbol. So now let's say EBL did store the value 255. We go to rule 5916 and update the 6502 notepad location pointer to point to the PCL variable. Now when I transition out of rule 5916, it doesn't matter what value is in the PCL variable, I'll write back 255, which is FF in hexadecimal. So at the cost of implementing 256 rules, I've transferred the value of EBL into PCL. Finally, I set up for an instruction fetch by asserting mread, and by going to rule 28 directly, I avoid the auto increment of the program counter. Let's see how this works altogether. Now the auto increment variable doesn't actually exist in our Turing 6502. This is just to show a functionally equivalent model. If we don't want auto increment in the real machine, we just jump directly to rule 28. And now that we understand what's going on, let's look at the actual machine doing it. So we're currently executing the instruction before the jump. Let's just get past that. And I'll stop it here. This is where the machine's fetching the force C opcode from the location 7BE0. And on the positive edge of clock, the next rule becomes 5654. And this is what we expect from instruction decode. Now we keep it running, and we can see it fetch the BC and the 7B. And now we see rule 28 with 7BBC, so the jumps occurred. Well, that's it for jump. Let's move on to branch. The branch instruction is a conditional jump. It may or may not change the flow of the program sequence. On the 6502, these branches are short range. In decimal, we can jump back 126 locations or forward 129 locations from the jump instruction itself. Because the final address is based on the current address, this is called a relative jump. On the 6502, there are 8 branch instructions. These branches consist of 2 bytes. The first one is the opcode, and the second one is the relative address. Each of these branch instructions checks a flag, which is a certain bit within the status register. Then it either decides to branch to a new address, or just move to the next instruction. Let's look at the status register on the real 6502 chip in a bit more detail. From a branch perspective, we're only interested in the N, V, Z, and C flags. So far, we've only seen the set decimal instruction in the last video, but there are a bunch of similar instructions for altering the other flags. Nearly every logical operation and arithmetic operation touches the flags in some way, and we'll look at this in more detail in future videos. There are 8 branch instructions, and each one has a unique arc out of Rule 28. There's branch plus and branch minus, which check the negative flag, which is bit 7 of the status register. BVC and BVS test bit 6 of the status register, which is the overflow flag. Branch if carry clear and branch if carry set test bit 0 of the status register, which is the carry flag. And finally, BNE and BEQ test the 0 flag, which is bit 1. Let's start with the BPL instruction and start with some code that represents what we want to do. First of all, we need to look at the status register and check to see whether bit 7 is set. If so, we don't take the branch and just go to the next instruction. But if bit 7 is clear, we want to take the branch. On exiting the branch code, I'll always make sure that the program counter points to the next instruction to be executed, whether the branch was taken or not. In this code, I'll set the auto increment to false, so it doesn't get incremented before the next fetch. For the BPL instruction, we go from Rule 28 to Rule 5380, and we set the 6502 notepad pointer to the status register. Then, once in Rule 5380, if bit 7 is 0, then we jump to Rule 5390, which is take branch. But if bit 7 of the status register is set, then we go to Rule 5388, which is no branch. Take a moment to think about this. This corresponds with the if statement in our C equivalent code. The BMI instruction is very similar. We just swap the take branch to a no branch, and the no branch to a take branch. Then we just repeat this for overflow, carry, and 0. The only thing that changes is the status register bit that's tested, and of course, the rule number. Now let's look at the no branch path. We know that the program counter is currently pointing at the branch instruction, so we need to skip this and the offset in the next location. In this implementation, we don't even fetch the offset if we're not going to take the branch. So no branch is quite straightforward. It's very similar to fast fetch, except we increment the program counter by 2 rather than 1. But take branch is a whole nother story. All branching instructions use the same code after reading the status register variable, but this is quite complex, and I'd like to see what the real CPU does. Fortunately, I have another playlist called Apple II Wire-by-Wire Build, and this contains a real 6502 CPU. The CPU is directly connected to an Arduino Mega, so I can snoop on all the bus transactions. So I'll look at some examples from the Pac-Man code to see exactly what it's doing. Now, it just turned out that BNE and BEQ were easy to find examples for, so I used these instead of BPL. Here's an actual trace from the Apple II Wire-by-Wire Build running Pac-Man, and I've just stopped after a BEQ instruction. Here we can see the branch if equal by 4 at location 7095, and here we can see it prefetching the next instruction at 7097, and here we can see it's resuming execution at 709B, which is 7097 plus 4. So let's look at some equivalent C code that might do this in the take branch arm of the if statement. First, we want to increment the program counter so that it's pointing at the relative address, which we sometimes also call the offset. Then I want to read this value from main memory and store it in a temporary variable. I'll use EBL in this case. Then I want to increment program counter again to point at the next instruction. And the reason I do this is that the offset's computed from that next instruction address. Then I add EBL to the address formed by program counter low and program counter high, and then I store this new address back in program counter low and program counter high. So far so good, but let's look at this example of BNE F0. The next instruction's fetched, but it's ignored. That next instruction is actually 60, which is returned from subroutine. So if it had been executed, I would have seen a whole lot of stack activity. Instead, execution resumes at 7BCB. But wait a second, if I pull out my calculator, I see that 7BDB plus F0 equals 7CCB, not the 7BCB that I see in the code. So what's going on? Well, to understand why the jump occurred this way, we need to briefly go over 2's complement representation. 2's complement is a way of representing negative numbers in binary, and I'll go over them in a lot more detail in the addition and subtraction videos. But essentially what we do is assign the top bit a negative number rather than a positive number. In this case, we assign bit 7 the value of minus 128. So now if we want to represent the value minus 16 decimal, we find that if we add minus 128 with 64, 32, and 16, we get the value of minus 16. So minus 16 decimal is represented as F0 in hexadecimal. But in 6502, the program count is 16 bits. So to add the offset in 2's complement form, we need to convert it to 16 bits also. So for a 16-bit number in 2's complement form, we assign the top bit the value of minus 32768. So to represent minus 16 decimal in 16-bit form, we start with minus 32768, then add 16384, and all of the powers of 2 down to 16. So now, minus 16 is FFF0 in hexadecimal. Now let's look at what happens when I add 7BDB to FFF0. Now I convert it back to 16 bits, and the result is 7BCB, which is what the actual CPU does. So to convert an 8-bit number into its complement form to 16 bits, we take bit 7 of the original number and copy it into all the positions above it, in this case bits 8 through 15. This process of copying these bits is called sign extension. Now the advantage of 2's complement is that we can just add numbers together, and the output will also be in 2's complement form. Hopefully you've had some experience dealing with signed and unsigned numbers. So now I need to add this sign extension into our C code. So the offset in 16 bits is just the offset in 8 bits, and then we test the upper bit, and if it's set, we add FF00, otherwise we add nothing. This is functionally correct, but it mightn't be the best way to implement it on the Turing 6502. So if we look at the first 3 instructions in the take branch arm of the if statement, we increment the program counter, load the system memory value into EBL, and increment the program counter again. So I need to do something with this value of EBL, so I'm going to convert it to state, or a rule number. But in all honesty, I don't really want to perform a 16-bit addition. Now if I look carefully, I see rules 5396 through 5523 are all the values where EBL is positive. So if I add EBL to PCL, it means that PCH will either be unchanged or incremented by 1. So you also notice that rules 5524 to 5651 are when EBL is negative. So when I sign extend EBL and add it to PCL, I know that PCH will either be unchanged or decremented by 1. So now I'm going to change my C code to look like this. Basically it says if EBL is positive, and the sum of EBL and PCL is greater than 255, then we have to increment PCH. And this second if statement says that if EBL is negative, and the amount that we want to subtract from PCL is greater than PCL, then we need to decrement PCH. It mightn't be completely obvious at first glance, but that's actually what the code's doing. So now for rules 5396 to 5523, we read the value in PCL and write back the value of PCL plus EBL. If this sum is less than 256, then we go to rule 28, but if it's greater than or equal to 256, then we go to rule 5653, which has the effect of incrementing the program counter. Then after that, we go to rule 28. And a similar thing happens for rules 55.24 to 56.51, where the offset is negative. We read PCL and write back PCL plus EBL, and this time if we cross the page boundary, we go to rule 56.52, which decrements PCH. Then in both pathways, we assert mread and go to rule 28. By doing this, we achieve the same outcome as doing a sign extended 16-bit addition, but in this case we only do 8-bit addition. Now let's step through the states with our ship and take note of the states that we go through for the B&E instruction. We take the branch, then we increment the PC, load EBL, increment the PC again, then convert the EBL value into a rule number. Then, by reading the PCL and having different write values per arc, we can essentially perform an addition by enumerating all the possible combinations of EBL and PCL, and assigning the write value to be their sum. What this means is the rulebook contains a big addition table. Then finally, we assert mread and go to rule 28. Now let's look at the real machine running the sequence. We start off in rule 28 at location 7BD9, and we fetch D0 into our instruction register. Then we cycle through rules 5386, 5390, 5392, 5393, 5395, and 5636, then back to 28. I'll stop it there, and now we can see the machine fetching the instruction at CBCB, so we've successfully completed the B&E instruction. And let's just compare it with our model again. Hopefully you'll see that we're stepping through the exact same sequence, which hopefully gives you a better idea of what the machine's doing. So there we have it. Jump and branch done. There are a lot of new concepts in this video, so don't be afraid to watch it again and again if necessary. And as usual, like, share, subscribe.